Okay. So I'd like to thank the organizers for putting together this interesting conference, and it's my first time in China, and I like very much the event and the city, and also would like to thank the Tsinghua University for welcoming us in its beautiful and vibrant campus. So this project I'm going to talk to you about is very much work in progress, and after a couple of years and a few papers, I'm still not sure what to make of it, and I hope you'll find this interesting, and as a result of this talk, I will also be motivated to think harder about it. So it all comes from the idea or the dissatisfaction with the current state of affairs in quantum field theory. So while QFT is, of course, much better understood than string theory or quantum gravity, it's still an unfinished business. And people keep finding new things in weakly coupled quantum field theory, but also, especially in strong coupling, what I think we need is a general method to solve strongly coupled QFTs. And the method which would not be based on extra assumptions such as SUSY, large N, integrability. And by solve, I mean just being able to compute reliably. And I think that to find such a method would require a combination of formal expertise of the kind which is present in this audience and an eye towards practical applications. And I think it's unlikely that a full analytic approach will work, so we will most likely need some sort of combination of analytics and help from a computer. So just to put everyone on the same page, I'm thinking of a general QFT as an RG flow, which originates from some UV CFT. And so the task naturally splits into two parts. First, you have to solve the UV CFT, and then you have to solve the RG flow. And as far as the first task is concerned, I think the rapid ongoing development in the conformal bootstrap make us hopeful that this could be a satisfactory solution. And today I'd like to talk about the second problem, which is much less understood. So to start the RG flow, you have to perturb the CFT. There are two types of allowed perturbations. You can either add a relevant operator to the action, or you can gauge. You can gauge a global symmetry by coupling the gauge field to the current of a global symmetry. And so this perturbation is relevant if dimension is less than 4, or in 4D if there is not too much charged matter. And once you do this, what happens at high energies, you can compute using perturbation theory, conformal perturbation theory. But at low energies, typically, unless you have a nearby fixed point, it's going to flow to strong coupling, and you need a non-perturbative method. And of course, there are already several established non-perturbative techniques on the market, so let me say a few words about them. The most well-known one is the lattice. So this technique has an advantage that it works in any number of dimensions. But it also has some disadvantages. So the first one, which is conceptual, is that in order to start a lattice Monte Carlo computation, you have to put the UV CFT on the lattice to begin with. So this is an extra step. And there may be even some CFTs for which it's impossible, which are impossible to realize on the lattice. And another drawback is that it's still really expensive to do this kind of computations. So for example, if you do 4-dimensional QCD with dynamical fermions, it's going to take you years of supercomputer time still, for example, to compute the spectrum of hadrons with a % accuracy. So it's you don't hear it often, but it's still incredibly expensive. It's not something that you or I can do. You have to dedicate your whole career to doing these sort of things. Another technique I'd like to mention is the matrix product states of tensor networks that Juan mentioned yesterday. So this technique is very efficient, extremely efficient for describing low-lying states of quantum spin chains with a finite correlation length. This is a generalization also for the critical state. And so it's a very efficient technique. Unfortunately, so far, it was computationally tractable only in 1+1 dimension. And again, if you want to describe a UV-complete RG flow, then you first to have realized your CFT as a spin chain. So again, it has this extra step. So another technique is the light cone. So this technique goes back to Weinberg and Wilson. And actually, Ken Wilson believed that the light cone would be superior. At some point, he believed that the light cone would be superior to the lattice. But it has not, this promise has not been realized. So this technique had its heyday in the 80s and 90s, where some non-trivial computations were performed, in particular by Igor, David, and in the 1+1 dimensional gauge theories with matter. And then it's been basically stagnating until some interesting recent work that I'd like to advertise by Ami Katz and et al., where progress has been achieved in improving the basis and to generalizing this technique to d larger than 2 and to non-trivial ultraviolet CFTs. So, and finally, I come to this truncated conformal space approach, which I would like to focus on for the rest of my talk. So this is, has been introduced a while ago in the work by Yurov and Zamolodchikov. And it's a relatively well-known technique in the condensed matter literature. And I think we should also pay attention to it. So I'll try to convince you. So the advantage of this technique is that it works directly in terms of the ultraviolet CFT data. So there is no need to realize your CFT in terms of some microscopic variables. Just if you solve the CFT, if you know the scaling dimensions, if you know the OP coefficients, then you can start already doing computations. So there are some disadvantages, or I would say lacunes, due to insufficient development. So I think all of them can be solved. So this technique so far has been developed only for relevant gauge vary perturbations, so no gauging. Most of the work has been done in d equal 2. And although the extension to the d larger than 2 is in principle straightforward, but there is only one paper by my collaborators and myself who try to do this. And as you will see, it works very well for strongly relevant perturbations, and not so well for more work is needed for weaker relevant and marginal perturbations. So what's this algorithm? What's this TCSA algorithm? So the first step is to put your CFT in a finite volume. So you take as a finite volume the d-1 dimensional sphere. So you put your CFT on SD-1 times r, so in the cylinder. And the sphere has a radius r, which is the infrared cutoff. And then, since this manifold is a while equivalent to the flat space, you know everything about this CFT on this manifold. So in particular, by the state operator correspondence, you know that the CFT Hamiltonian is diagonal with energy spectrum being given by the scaling dimensions of the CFT divided by r. So that's very useful. Now, as a second step, you have to perturb your Hamiltonian. So you add to the CFT Hamiltonian the perturbing operator integrated over the sphere. So the CFT Hamiltonian is diagonal, and this is going to cause some non-diagonal mixing between the states. And so the perturbation matrix elements, these ones, can be, by mapping to the flat space, can be expressed in terms of the OP coefficients of the CFT. So that's so this procedure gives you the full Hamiltonian of your problem as an infinite dimensional matrix, which has a diagonal part, which is the CFT Hamiltonian, and the off-diagonal part expressed in terms of the OPE coefficients. So it's given completely in terms of your CFT data. And the inappropriate units, there is, you see that the perturbation is small if you are at small radii. So mu is the mass scale of your flow, and then if this mu r parameter, dimensionless parameter, is small, then it's a small correction. And if it's large, then you're at strong coupling and you're approaching the infrared regime of your flow. So that's how it works. So this matrix is infinite dimensional. And as a next step, you truncate it. You truncate your Hilbert space by including only operators with scaling dimension below some cutoff delta max. Once you've done that, you diagonalize your truncated Hamiltonian on a computer. It's a finite matrix. And you get a spectrum, or an approximation to the spectrum of your Hamiltonian in finite volume. So that's how the algorithm works. And it's important to understand why this extends the range of validity. So if you were just to do the direct perturbation theory, conformal perturbation theory, then you would only be able to describe the radii of the cylinder much smaller than the mass scale of the RG flow. And so that would not be enough. That would definitely not be enough to access the infrared regime of your flow and, for example, to measure the particles, particle masses, if the flow is massive. So, however, if you treat the states below delta max exactly, by diagonalizing the sector exactly, you raise the effective UV cutoff of the theory from 1 over r to the lambda UV, which is of the order of delta max over r. So this is the natural energy scale. And so given that the expansion parameter is going to be mu over lambda UV, this means that you can go now to the radii, you can trust your calculation to the radii, up to the radii of the order of delta max times mu inverse. So this means that you extended the range of validity of your calculation, and now you can hope to access your infrared physics if the delta max is much larger than 1. So this is a naive but intuitive argument why this is supposed to work. Well, this is naive because, so I have not discussed here, I have completely neglected here the issue of UV divergences that you think you should encounter at some point. And also, this issue of UV divergences turns out to be related to the issue of the rate of convergence of this method. So how accurate is your computation going to be? So, but before we turn to this, suppose that this works, what do you expect to see? Well, so as a function, so let's plot the energy levels of the theory as a function of the radius of the sphere. And then there are going to be two regimes. As I said, there's going to be a regime of small radii where you're going to be close to the UV CFT, and there's going to be an infrared regime at large radii. So at small radii, all energy levels are going to scale like the CFT energy levels, delta I over R. So what happens at large radii? So first of all, let's look at the ground state. So here I set the Casimir energy to 0 in this plot, just for convenience. So physically, we expect that at large radii, the ground state energy is going to scale with a finite energy density. So there's going to be some vacuum energy density, rho vac, times the volume of the sphere. So that's what you expect. Now, concerning, so what are the other energy levels going to do? For example, what is the first energy level is going to do? Well, at large radii, you expect it to asymptote to a line which is going to stay finite distance away from the ground state energy. And this is going to give you the measure of the mass gap if the flow is the infrared massive. So this is going to give you a way to measure the particle masses of the theory. And then the second energy level is going to asymptote to twice the mass gap if there are no other particles. And then there's going to be some lines which will give you 2 particle states with relative angular momentum on the sphere, and then there are going to be 3 particle states, and so on. So you will see all of this structure of the spectrum by doing this calculation. So that's what you expect if everything works. And so what do you see? Well, here I'm going to show you one of the earliest calculations done by this method by Yurov and Alyosha Zamolodchikov in '91, who studied the 2-dimensional Ising model perturbed by the magnetic perturbation. So the nice thing about this flow, since they were just exploring the method, they wanted to check it against something that they knew, so they took an integrable flow. So this flow is integrable, and you know analytically the ratios of the particle masses in this flow. And so they did this calculation. They observed precisely the picture that I described. So it was in 2D, so the ground state energy density was scaling linearly. Then they had a 1 particle state. Then they had another particle here because this theory has more than 1 stable particle. And the masses that they extracted, so basically with 1% accuracy, they extracted all the masses in agreement with the exact results. And the amazing thing is that they were able to do this by diagonalizing only 34 times 34 matrix. So it was a really easy calculation if you think about how much information it gave you. And so why did this work? So when I first saw it, I got completely hooked, and I wanted to understand why this works. Is this somehow related to the fact that the flow is integrable, that they managed to do this? As far as we understand, no. This is not related to the integrability in any way. And so if you want to understand this, you have to understand where the error comes from. So what is the source of the error in this method? It's the truncation error. So this error is caused by the fact that there is a mixing. So you truncated the Hilbert space, you threw out the high energy states, but of course they mix. There is some mixing between these states and the low energy states that you kept. So it's this mixing which causes the error, which you neglected. And this mixing can be estimated by studying the 2-point function of the perturbing operator between 2 low energy states. And since you're interested in the high energy tail of this matrix element, it means that you have to study this 2-point function in the OPE limit, where these 2 points approach each other on the sphere. And so this can be done, and you can get analytic understanding of the convergence rate of this method, which agrees with what you see numerically. And so the convergence rate is given by, in terms of this expansion parameter mu over lambda uv to the power 2D, 2 space-time dimensions minus the dimension of the perturbing operator. So that's, this is what you get. And so you see from this formula that the method is going to work best if the dimension of the perturbing operator is strongly relevant. And so this explains why it worked so well for the flow that I showed, where the dimension was 1/8. So this power was really high. And that's why it converged really fast. But also, you see that according to this formula, for the dimension of the perturbing operator larger than d over 2, this naive truncated method is not going to converge. So you expect to see divergences. So this is related to the issue of UV divergences common in quantum field theory. And so the first divergence occurs in the vacuum energy density, and this divergence is visible already in the second order perturbation theory. So this perturbative correction to the vacuum energy density is UV divergent if the dimension of the operator is larger than d over 2. And it's the same divergence which is going to affect a non-perturbative technique as well. So this divergence is not so consequential because it cancels when you measure the particle spectrum, when you take the energy differences. But if you raise the dimension of the operator higher, then you're going to encounter more important divergences which are related to the coupling renormalizations those are not going to cancel, so you have to really add counter terms to reach the continuum limit. So this is all just as in usual QFT, except that working with a somewhat unusual regulator. So this cutoff in the energy on the cylinder is not a usual regulator. All right. So what are you supposed to do? Well, actually, even if the dimension of the perturbing operator is smaller than d over 2, so that the naive truncated method converges, you are going to be better off if instead of truncating everything naively, you try to integrate out the high energy states. So if you do that, which would be analogous to what people do in QCD when they construct improved actions to work on the lattice. So if you construct this sort of improved Hamiltonian, which you can do analytically, then you're going to see that the cutoff dependence is going to be reduced. And so you can do this perturbatively order by order. And this has been done, so at lowest non-trivial order, it has been done in our work. So that's something that is useful to do. And, well, I'm coming to my conclusions, basically. So you see it's very much an ongoing enterprise, which I think is very, very promising and fascinating. But at present, it's not yet 100% clear if it's going to become competitive, say, with the latest QCD in 4 dimensions. So it's been not yet sufficiently developed. But I think it deserves to be investigated further. So this technique, if you wish, it generalizes the well-known Rayleigh-Ritz method. So in quantum mechanics, there's a Rayleigh-Ritz method, which is the best method to solve quantum mechanical problems which cannot be exactly solved, from quantum mechanics to quantum field theory. So that's what we are doing here. We are just taking seriously the idea that quantum field theory is a quantum mechanics of infinitely many degrees of freedom. And there's a lot of work. There has been a lot of work and applications in the condensed matter literature. So I really recommend all this literature, which is cited in our papers. So that literature mostly focused on applications, while I think it's important to develop the conceptual side of things a bit further. And in particular, it's really important to develop further this RG improvement technique, which I mentioned, to extend the method to D larger than 2 dimensions, and to extend it to gauge theories. And finally, the last point I'd like to make is that, as you know, in CFTs, the number of states grows exponentially with energy. So there is an exponential of a power of dimension, and this power depends on is 1 over d. So this is potentially damning for the method, because as you raise the cutoff, your Hilbert space explodes. However, somewhat amazingly, you find empirically, when you do this sort of computations, that only a very small fraction of all of these states turns out to be important, has significant weight in the wave functions that you find. So this is not really very well understood, and I think it would be really important to understand this theoretically, because this would lead to a dramatic improvement in the power of this approach. Thank you.
When you do this improvement, as you said, do you effectively reduce the dimension of the perturbation? What kind of improvement is it?
So at leading order, this improvement just amounts to finite cutoff-dependent renormalization of the couplings of your Hamiltonian. At higher orders, you keep adding to the Hamiltonian some counter terms, which are all formally power-like suppressed, so you wouldn't normally bother about these counter terms, but in this numerical approach, it's important to take advantage of them. The funny thing is that since this regulator is a non-standard regulator, it's a non-local regulator in a sense, and it also breaks Lorentz invariance. So you encounter counter terms which you would not normally encounter in perturbative quantum field theory.
Second, in your comprehensive list of non-regulative techniques in quantum field theory, you left out one kind of new technique. I wonder what your opinion is in the resurgence, trying to make analytic and potentially numeric sense out of perturbation.
Well, I think it deserves attention, definitely. I left it out because, as far as I know, it has not yet achieved explicit calculations of the type that have been done with other techniques. So I think it's a challenge for them to try to sit down and just do something that can be compared with other numerical techniques, rather than just to explore the formal structure of the method.
Second, so if you pretend that there is a holographic description of this flow, even hypothetically, but maybe there is a way to make precise sense of it, would this d over 2 be related to d of or something that you could recognize holographically?
Well, it's definitely, this d over 2 is going to it's very generic, so it's going to affect any flow, holographic or not, because it's just, I'm not sure it's related to the BF bound, though. It's just, it's related to the fact whether the vacuum energy density is observable for this flow or whether it's UV sensitive quantity. And this is just related to the dimension of the perturbing operator. So I think it's pretty generic.
So some RG flows lead to other CFTs, right? So in this method, is it like very easy to tell if it's going to go to another CFT or if it got some of the theory? Or maybe it's not a good question.
Oh no, it's a perfectly valid question. Yeah, it's I focused here on the massive flows, but if you flow to a CFT instead, of course, this is possible. And in fact, in our work, we studied, in the scalar field theory, which we studied in our work, as a range of parameters, there was a quantum phase transition where it did flow to a CFT in the infrared. Then you see that as you approach the CFT point, you see that the mass gap goes to 0, and then you see that the energy levels, instead of going to a constant, they scale in the infrared as 1 over r, with different powers, which are related to the infrared CFT scaling dimensions.
When the operator is slightly irrelevant, then there is a kind of a formal perturbation theory argument that tells you that quite generally you're reaching nearby CFT. So maybe as you vary the dimension from slightly irrelevant to irrelevant, something like that.
Well, it's a bit paradoxical, yeah. From the point of view of conformal perturbation theory, the slightly irrelevant operator is the very simple case. From the point of view of this method, it's a maximally complicated case. So it's something has to be done about it.
Thank you.
We have time for one more question.
Hi, Slava. Do you have some understanding or some hints for which states are going to be more important? I'm talking about the last transparency. Which states are dominant for TCSA?
Well, empirically, what you see is that, so if you divide your states into primaries and if you divide your bases in primaries and descendants, then you find that if a given primary contributes, then all of its descendants are going to contribute with power-like fall-off. While the decay in the dimension of the primary is much faster. So it looks like you need to have very few primaries to already describe the physics pretty well. Well, you need to keep all the descendants of the primaries that you keep.